Some industrial explosions are violent enough to level an entire facility in seconds. Their power is driven by the rigid laws of physics. This is the terrifying science of a boiling liquid expanding vapor explosion, a BLEVE, and why it remains a destructive force in industrial safety. This video is for educational purposes only and is not a substitute for formal process safety training or engineering analysis. This event is a massive physical explosion triggered by the catastrophic failure of a pressure vessel holding a superheated liquid. If a standard tank of compressed gas ruptures, the pressure releases linearly as the gas vents. However, when the vessel is filled with a pressurized liquid, the rupture triggers a violent liquid-to-gas phase transition. The liquid flashes into vapor almost instantly. Liquefied petroleum gas, or LPG, is the most common substance involved in these disasters, appearing in roughly 59% of historical BLEVE records. But the data reveals a broader hazard. Strictly non-flammable water accounts for 11% of these explosions, and cryogenic liquids, like liquid natural gas, account for 4%. This statistical spread attributes the destructive power to the physical phase change of the liquid, rather than the flammability of the fuel. To prevent an entire facility from being leveled, safety professionals must look past the flames and understand the underlying thermodynamics of that phase change. This phase change diagram shows the pressure-temperature relationship governing this balance, with the saturation curve separating liquid and vapor. Past equilibrium lies a critical failure threshold, the superheat limit temperature, or SLT, typically occurring at roughly 88 to 92. The liquid acts as a heat sink, absorbing the thermal energy and cooling the wetted metal walls it touches. The structural vulnerability exists just above the liquid line, in the unwetted vapor zone known as the ullage space. Unlike the liquid below, the vapor in the ullage space is a poor thermal conductor and cannot pull heat away from the steel shell. Without that cooling effect, the unwetted steel rapidly absorbs the fire's energy. As the metal exceeds 650 degrees Celsius, it loses its tensile strength. Standard pressure relief valves cannot prevent failure in this scenario. The thermally weakened steel of the ullage space simply cannot withstand the internal pressure anymore. The high internal pressure pushing against this degraded steel results in a catastrophic longitudinal ductile tear. At the moment of the tear, the vessel's internal pressure drops to atmospheric levels almost instantaneously. This exposes the metastable liquid to extreme thermodynamic shock, leaving it violently superheated relative to the new, lower pressure. Because the liquid is at or above its superheat limit temperature, the entire mass undergoes spontaneous, explosive boiling all at once. The liquid flashes into vapor, expanding its volume 200 to 300 times in a matter of milliseconds. This rapid volume displacement acts like a physical piston slamming against the atmosphere, generating a massive mechanical overpressure blast wave. That shock wave tears the pressure vessel apart, rocketing high-velocity steel fragments across the facility. If the flashing liquid is a flammable hydrocarbon, the rapidly expanding vapor cloud mixes with atmospheric oxygen and ignites at its turbulent edges. This radiating fireball often causes significantly more fatalities and triggers more secondary cascading failures than the initial mechanical blast. Transport activities carry the highest risk for a BLEVE because of the likelihood of derailments and impacts followed by fire exposure. In static facilities, the root cause is often a layout failure, such as allowing leaked flammable liquids to form pool fires directly beneath pressurized tanks. Relying solely on pressure relief valves is an engineering error, as they cannot protect the unwetted ullage space from thermal weakening. Modern mitigation involves passive controls, like intumescent fireproofing insulation and coatings designed to delay metallurgical failure. Active controls include automated water spray deluge systems and monitors specifically positioned to cool the vessel's vulnerable upper dome. Proper plant spacing and intelligent grading that drains hazardous liquids away are the foundational defenses against these thermal threats. A safely engineered facility maintains a quiet, stable thermodynamic balance. When that balance fails, the resulting devastation leaves a leveled, smoldering footprint. A BLEVE triggers at the exact millisecond thermodynamics outpace mechanical containment, functioning as a predictable physical consequence of specific vessel failure conditions. Understanding the physics of a BLEVE is the first step toward preventing one. Never underestimate the hidden power inside a pressurized vessel. Respect the physics, and you can prevent the boom. If you want to learn more about process safety, industrial disasters, and OSHA rules, subscribe to the HSE Study YouTube channel.